welcome to another module in this massive open online course on estimation for wireless system. So, we are considering currently the maximum likelihood estimation of a vector parameter h bar, and we have shown that the maximum likelihood estimate, which is also the solution or that corresponds to the minimum of the least squares cost function. This maximum likelihood estimate or the least squares estimate h hat is given as your h hat equals x transpose x inverse x transpose y bar, okay. And this matrix x transpose, we have called this matrix as the pseudo inverse of x. Remember, this is called the pseudo inverse. Okay. And this we have also called the ML estimate of the vector parameter. This is your ML estimate or LS, that is least squares estimate. Now, let us explore the properties of this maximum likelihood estimate. Let us now explore what we want to do is we want to explore the properties of this we would like to explore the properties of this maximum likelihood estimate, which is basically h hat equals x transpose x inverse times x transpose y bar, where y bar is of course the vector of observations and the matrix x is the pilot matrix for this multi antenna system, correct. Now, recall again, let us go back to our system model. Recall that our system model is y bar equals x h bar plus v bar. This is basically your system model. Where v bar is a Gaussian noise vector. Remember, this vector contains Gaussian noise samples. So, this is a Gaussian noise vector. Now, y bar, which is equal to x h bar plus v bar, it is related in an affine fashion to v bar, that is, it is a linear transformation of v bar, basically v bar itself, plus a constant, shift by a constant, that is x h bar. Therefore, this is known as an affine transformation, right. So, y bar is basically related in an affine fashion, or y bar equal to an affine transformation of v bar, which basically implies linear in v bar, that is linear transformation of v bar plus a constant shift. Now, affine transformation, now Gaussian variables remains Gaussian under an affine transformation, implies y bar is basically equals a Gaussian vector. So, what we are saying is basically the following thing: if I take a Gaussian random variable, if I scale it and if I shift it by another constant, right, that is I consider an affine transformation of this Gaussian random variable, I basically get another Gaussian random variable, right. So, the Gaussianness remains invariant under an affine transformation. Now, I have y bar equals x h bar plus v bar is Gaussian. So, I am taking v bar, shifting it by x h bar, therefore, y bar is a Gaussian vector, alright. So, let us start with that first, that is the observation vector y bar is Gaussian. So, y bar, which is your observation vector. So, let me repeat that. Observation vector y bar is Gaussian. Now, if you look at h hat equals x transpose x inverse x transpose y bar. This is basically a linear transformation of y bar, what is this? This is a linear transformation of the vector. This is a linear transformation of the vector y bar, and hence since y bar is Gaussian, and linear transformation of a Gaussian vector results in another Gaussian vector h hat is Gaussian in nature. Since the linear transformation of a Gaussian vector results in another Gaussian vector, the estimate h hat is a Gaussian vector. So, that is the first thing that we have established, that is h hat is the estimate of the vector parameter h, that is h hat is a Gaussian vector. Okay, that is the first thing. Now, second, let us look at h hat equals x transpose x inverse x transpose y bar, but recall your y bar equals x h bar plus v bar. So, I can substitute that over here now. So, I have x transpose x inverse x transpose times, instead of y bar I will substitute x h bar plus v bar, which is basically y bar, and now expanding this I have x transpose x inverse x transpose times x h bar plus x transpose x inverse x transpose v bar. Now, if you look at this quantity over here, x transpose x inverse times x transpose x, this is identity. Therefore, I simply have identity times h bar, which is h bar, plus x transpose x inverse times x transpose v bar, and this is your h hat. So, the least squares estimate h hat can be expressed as h hat equals h bar, the original parameter, unknown parameter vector, plus something that depends on noise, that is x transpose x inverse times x transpose v bar. Now, again recall V1, V2, Vn are IID 0 mean Gaussian random variables, implies expected value, since there is 0 mean, expected value of V1 equals expected value of V2, so on and so forth, that is expected value of each random variable equals 0. And therefore, now if I look at the expected value of this vector as a whole, that is, if I look at the expected value of this Gaussian vector v bar, that is the noise vector v bar, that is equal to basically your expected value of your vector comprising of components v1, v2, vn, which is basically, now if I take the expected value inside, that is nothing but the expected value of V1, expected value of V2, so on, expected value of Vn, and each of these is basically 0. So, this is the n dimensional 0 vector, and this is fairly natural again. That is what we are saying is, if you look at the noise vector, each of the noise components V1, V2, Vn, each of these Gaussian noise components has 0 mean. Therefore, the expected value of the vector V bar is 0, that is, it is the 0 vector. Now, I can use this to simplify the expected value of our estimate h hat. Recall that h hat equals x transpose x inverse x transpose, that is equals your h hat equals h plus x transpose x inverse x transpose V bar, which means expected value of H hat equals expected value of H plus x transpose x inverse x transpose V bar, which is basically nothing but, now H bar is a constant. So, I can take that outside as H bar plus expected value of x transpose x inverse x transpose V bar. And now again the pilot matrix X is constant. So, I can move the expectation inside. I have x transpose x inverse x transpose expected value of V bar, but the expected value of V bar is the 0 vector, that is the n cross 1 0 vector. Hence, as a result of that, basically this quantity which is x transpose. So, let me just write that down, maybe it is h bar plus x transpose x inverse x transpose 0 bar, this quantity is 0. Therefore, what we have again similar to what we have seen many times before, that is your expected value of the vector estimate H hat equals H, and this is basically your unbiased property. That is what we are saying is something very interesting, and which we already said before in the context of a scalar estimate, that is H hat is the estimate and it is a random quantity. Remember, it is not a deterministic quantity. Remember, we already said H hat is a Gaussian in nature, it is a Gaussian vector. However, if I look at the average value of H hat, that is expected value of H hat, that is equal to H bar, that is the expected value is basically equal to the true value of the underlying unknown parameter. Therefore, such an estimator is known as an unbiased estimator, and the estimate is known as an unbiased estimate. So, this maximum likelihood estimate or the least squares estimate is unbiased in nature. That is the first thing that we have established. So, the ML, so your ML or basically least squares estimate the ML or least square estimate is unbiased. That is the first thing. Now, what we want to do, the second thing that we have to do is find the variance or the covariance. Since this is a vector, right, for a scalar random variable we find the variance, scalar estimate we find the variance. Since this is a vector, let us now find the covariance of the estimate. So, let us now find the covariance of the estimate. Let us now find the covariance of the estimate H hat. That is, the covariance of the estimate is defined as, remember, H hat minus the expected value of H hat times its transpose H hat minus the expected value of H hat slightly H hat minus expected value of H hat transpose, and now realize that expected value of H hat is basically your vector H bar, because the vector is, the estimate is unbiased. So, basically that is basically nothing but your expected value of H hat minus H bar times H hat minus H bar transpose. Now, we already seen that H hat, look at this, H hat equals H bar plus x transpose x inverse x transpose V bar. So, what I have here is basically I will use the property H hat, or let me use the property H hat equals H bar plus x transpose x inverse x transpose V bar, which basically implies that, now if you look at this, this basically implies H hat minus H bar equals x transpose x inverse x transpose V bar, and now if I substitute that in this expression over here, I will get the covariance is equal to expected value of h hat minus h, that is x transpose x inverse x transpose V bar times its transpose, that is x transpose x inverse x transpose V bar transpose of this quantity. And now I can simplify this quantity can be simplified as follows. This is the expected value of, well, the first quantity I can take it as it is, x transpose x inverse x transpose x V bar. The second quantity transpose of that is V bar transpose x transpose transpose, which means x transpose x inverse transpose, that is again this is a symmetric matrix, the inverse is also symmetric, therefore, the transpose is itself. Now, I can move the expectation operator inside. When I move the expectation operator inside, what I have is basically I have your x transpose x inverse expected V bar times x transpose x inverse, and now this expected V bar transpose, this is nothing but covariance of the noise. Remember, expected V bar transpose is the covariance of the noise vector V bar, and remember again we are considering 0 mean IID Gaussian noise elements V1, V2 up to Vn, which means the covariance matrix is sigma square times identity. That is also something that we have seen before. Remember, this is we are considering 0 mean IID Gaussian noise elements V1, V2, Vn of variance, that is each noise sample has mean 0, variance sigma square, and these noise samples are independent, which implies the covariance expected V bar transpose is equal to sigma square times identity. That is the noise covariance expected V bar transpose considering 0 mean IID noise samples of mean 0 and variance sigma square is basically sigma square times identity. And now I can substitute that in this expression for the covariance of the estimate h hat to simplify it further. And now once I substitute that, things you can see it has a nice form. This is basically reduces to equal to x transpose x inverse x transpose times the covariance, which is sigma square times identity times x transpose x inverse. And now you can clearly see I can bring the sigma square outside, that is a scalar quantity, and identity times any matrix is the matrix itself. So, this reduces to x transpose x transpose x inverse. Now, you can see that this I have an x transpose x inverse, I have an x transpose x. So, basically this is identity. So, this is sigma square times what I am left with is x transpose x inverse, and this is the covariance of the estimate. What is this? This is basically your covariance of the estimate h hat of the vector parameter. And finally, to summarize, we already said three things. H hat is a Gaussian parameter, h hat has mean, this is an unbiased estimate, that is expected value of h hat is the parameter vector h bar, and its covariance is sigma square x transpose x inverse. Therefore, now I can neatly summarize this as h hat is basically it is Gaussian it is a Gaussian vector, we denote it by this n with mean h bar covariance x transpose x inverse. All right. So, this summarizes the behavior of the estimator, which is Gaussian with mean h bar and covariance sigma square x transpose x inverse. And now also realize something interesting, the diagonal elements of the covariance matrix correspond to the variances of the components of the vector estimate. That is, if you look at the ith estimate variance of the ith element, variance of ith coefficient hi, that is, or rather variance of the estimate of the ith coefficient, that is expected value of hi minus hi square. This is the diagonal element of the ith diagonal element of the covariance matrix. This is sigma square x transpose x inverse, that is the I comma ith element, that is the ith diagonal element or the I comma ith element of this matrix, which is basically nothing but sigma square is a constant. So, I can bring that out, that is I take the ith diagonal element of this matrix. This is what is this? This is the variance of the estimate of the ith coefficient. This is the variance of the estimate of the ith coefficient in the vector parameter h hat. All right. So, what we have seen in this module is basically we have looked at the least squares of the maximum likelihood estimate h hat, which is equal to x transpose x inverse times x transpose y bar, and we have simplified, we have explored the properties of this vector estimate, and similar to before we have said that first this vector estimate, it is a Gaussian vector. Remember, unlike the scalar estimates that we have considered previously, now we are considering a estimate, a vector estimate or an estimate of a vector parameter. So, what we have is a Gaussian vector which is unbiased, which means the average value of this estimate h hat is basically the underlying parameter h bar, and the covariance is basically given by sigma square x transpose x inverse, where x, remember we said, is the pilot matrix. All right. And finally, we also said the variance of the ith, the variance in the estimate of the ith coefficient is given by the ith diagonal element or I comma ith element of this covariance matrix. Right. So, that basically succinctly summarizes the properties of this maximum likelihood estimate, and we will explore other aspects in subsequent modules. Thank you very much.